Yeah, so good evening all of you. Welcome back to this series of engineering mathematics basically, and in today's class we'll be looking again onto the multivariable calculus, and we will extend our discussion from yesterday's class. Okay, so let's see. Before I straight away start, so lecture number 3 of multivariable calculus. So I suggest you, or basically advise you to scan this QR code and get in connected with the Telegram channel so that you won't be missing any update. Okay, so you'll be having quick touch with the concepts, and you won't be able to miss any content that's flowing out here because of the regular updates on this channel. Okay, so I advise you and strongly recommend you to just join this Telegram channel to get updated. Okay, and of course this is the code for my Telegram channel. Again, it's maintained by me and my students at PW. So if you feel any help, or if you need any update or any information, then you can post it here. Either me or some of my students will be definitely, it's like a group to build together. So in this group you'll be getting information for the for all your queries actually. Okay, and also again I suggest you to advise this, basically advise you to install this Unity app actually, so that you'll have like a one-stop place for all your doubts and also key points as well. Okay, so if you type exclamation doubt, and then if you type the doubt, then you can have the this particular doubt, whatever you got at the point of learning the concept, will get stored at a particular place. Okay, similarly here for the exclamation notes you can write, and you can start typing the comment actually, so it gets saved in the notes tab obviously. Okay, so let's have a quick review of the last lecture, what we are talking in the last lecture. So in the last lecture we were looking at multivariables. Of course here we are talking about two variables, two independent variables in general. So we were talking about limits in 2D, limits in 3D in general, because x and y are independent variables and z is the dependent variable. Okay, so z is basically some function of x comma y. In the last class I have given you the coordinate system, and I have also shown you how the values of z can vary depending upon the xy plane. Okay, values of x and y. Similarly we have also seen the definition of continuity, and we have looked at partial derivatives. Okay, so we have seen partial derivatives and how do we differentiate a function with respect to x, y, these things. And also we have seen something called, very important thing in fact, chain rule of differentiation. Okay, so chain rule of differentiation, chain rule of differentiation, and this tells you if f is some function of x1, x2 and so on till xn, then this implies the change in f due to change in all these variables is basically will sum up the changes due to the individual variables, and we put them together. So summation I equal to 1 to n dou f by dou xi multiplied with dxi. Okay, so this is what you get, of course. And we have seen in general that the total change in f is brought by the changes due to all these variables, and we sum them up. Okay, so these are the things we have seen, and of course I have told you the techniques for calculating the partial derivatives with respect to, say for example, p is with respect to x, q is with respect to y. Normally we denote this partial derivatives with this p and q. The other shorthand notations is like fx, fy. Okay, so fz, we have things like this where it means of course dou f by dou x. Okay, and similarly this means dou f by dou y. All these are different notations for denoting the partial derivatives, of course. Okay, so this is dou f by dou z actually here. Okay, yeah, welcome back. And we also have some certain examples, some questions actually to make you familiar with the calculation of the partial derivatives. And of course you are already familiar in calculating these partial derivatives. Let's see, if you want to calculate for example dou square f by dou x square. Okay, it's the second derivative. This is nothing but dou by dou x of dou f by dou x actually. Okay, similarly if you have something like dou square f by dou y square, this is something like dou by dou y of this function dou f by dou y again. So basically you know how to calculate the first order derivatives. Then again by applying dou by dou x once again, or applying dou by dou y once again, you can calculate dou square f by dou x square and dou square f by dou y square as well. Okay, and also if you have something like dou square f by dou x dou y, this tells you dou by dou x of dou f by dou y. Okay, so this is how we can calculate. So these are the things which I have given you in last class, of course, and also I have given you some homework question. Okay, so in today's class we are going to look at partial derivatives and of course the Euler's theorem, and also Taylor's series in two variables. Okay, normally in single variable calculus I have expanded the series basically about one particular variable, but here we'll go for two variables, and we'll also discuss the concept of maxima and minima as well. Okay, of course I'm not sure whether I can discuss this constrained maxima and minima in today's class, but I'll try to give some glimpse of unconstrained maxima and minima actually. Okay, so let's start with this partial derivatives and Euler's theorem. But before we go here, I've given you some homework to solve. So have you solved it? Hello, answer this question. If f is equal to y power x, the value of dou square f by dou x dou y at x equal to 2, comma y equal to 1 actually. Come on, do this. So if you have already solved this question, then enter the answer. This is a homework question, one of the homework questions that I've given you in the last class. Okay. So the answer is coming out to be 1, maybe. So if you have already solved, then enter the answer because it's a homework question. So I expect you to solve this. 1 is the answer. Is it? Okay, maybe. I'm not sure. Let's check it out. How much it's going to be. So, hello. Let's solve this question. Then, given f is equal to y to the power x. Okay. So y to the power x. And you want to calculate dou square f by dou x dou y. Okay. So dou square f by dou x dou y. If you calculate this, basically this is ultimately equal to dou by dou x of dou f by dou y. Okay. Now, when you treat this x as constant, the term become x into y power x minus 1 and things like that. So what I can do is just a bit of manipulation, since this is a smooth function of course, and dou square f by dou x dou y is same as dou square f by dou y dou x. So which is equal to dou by dou y of dou f by dou x. This is what I want to do actually. Okay. So if I calculate this value or if I calculate this value, the answer would be same. Okay, no issues. So let's calculate it because it slightly reduces the calculation. That's all. Okay. So let's do it. This is equal to dou by dou y of dou f by dou x. So what is dou f by dou x? If you are differentiating this with respect to x partially, this y is taken as a constant. So this y power x is of the form some a power x form actually, correct? And you know the derivative of this y power x into ln y is what you get. Okay. So y power x into ln y, that's what you get, because if y is constant, it's of the form a power x log a to the base e is the derivative. So like this. Now when you differentiate it with respect to y, of course x is constant. So if x is a constant, it's like x into, or first of all, first function into derivative of the second function plus second function into the derivative of the first. So if x is constant, you can write this as x into y power x minus 1, of course. Okay. So clearly this is also, if you cancel this y, it becomes minus 1. So y power x minus 1, if you take common, then you have 1 plus x times ln y. This is what you would have actually. Okay. Now you want this value at this point x equal to 2 comma y equal to 1. So therefore d square or dou square f by dou x dou y at x is equal to 2 comma y equal to 1 is equal to, so y equal to 1 is equal to, so if you replace x equal to 2 and y equal to 1 power 2 minus 1 times 1 plus x. So what is the value of x? 2 times of ln 1 actually. Okay. So this is the value. So ln 1 value is 0, of course. This is 0. So 0 into 2 is 0. This is 1. Again 1 power 1 is 1. So 1 into 1 plus 0. So the answer is 1 actually. Okay. So this answer is 1, of course. So 1 is the correct answer. Okay. Good evening, Steven, 7 stars. So many of you might ask me why I have actually converted this, why I have not directly started with this. If I have directly started with this, I would have got something like dou by dou x of dou f by dou y. So if you treat this x as a constant, you have x into y power x minus 1. Now when you are differentiating this, it's something like first function into derivative of second, and when you are differentiating with respect to y, this y is constant. Here you have y power x minus 1 into log y. Of course you'll get the same result, but it's slightly I felt easy it could be. So second function into derivative of the first. So if you take y power x minus 1 common, again you have 1 plus x ln y. Okay. So both give you the same answer. It doesn't matter, the answer is 1. So in case of partial differentiations, please make a note, as long as these functions are differentiable, the order of differentiation, when you have multiple terms here, like dou square f by dou x dou y or dou square f by dou y dou x, these two things give the same value actually. Okay. So there is no issue. The correct answer is 1. Let's check if some of you have entered 1. Okay. Oh, okay. Shravan, Ashwini Kumar Biswal, good. So let's go to the next question. So let's solve this question. If f of x y z is equal to x square plus y square plus z square whole power minus 1 by 2, then dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square. This is again some question which I have given you. So enter in integer, 30 seconds, enter the answer. If you have solved this question correctly, you would have entered the answer. Do it. Come on, solve this question. F is equal to this x square plus y square plus z square whole power minus 1 by 2. Then del square f by del x square plus del square y by del y square plus del square f by del z square actually here. Okay. So normally, since, okay, you can enter the answer meanwhile. Since I have not taught you vector calculus, I'm just doing this solution manually. Okay. If you know vector calculus, solving this question would have been very simple. Like simple in the sense very small in size. The solution would have been very small in size, but now it's slightly elaborative. Look. Solution. Given f is equal to x square plus y square plus z square whole power minus 1 by 2. So I can write it as 1 by root of x square plus y square plus z square, of course. Okay. So this is what I would have written. Then what is dou f by dou x or fx actually? So if you differentiate this function with respect to x, you would get 1 by, first of all, derivative of 1 by root x is, this is, okay, see we have 1 by 2, it's fine, we'll keep 1 by 2 here. X square plus y square plus z square whole power minus 1 by 2. So if you differentiate with respect to x partially, so first of all, some function power some fraction or some quantity you have, so minus 1 by 2 into x square plus y square plus z square times of this power minus 3 by 2 into, because you know n into function power n minus 1, so that's why minus 1 by 2 into x square plus y square plus z square whole power minus 1 by 2 minus 1, so which is minus 3 by 2 into the inner derivative of this function, which is 2x actually. Okay, so this gets cancelled. So you have minus x into x square plus y square plus z square whole power minus 3 by 2, of course. Okay, that's the value. Now once again, if you calculate dou square f by dou x square, dou square f by dou x square, so if you differentiate this, minus sign you take common, then first function into derivative of the second function with respect to x, that gives you minus 3 by 2 times of x square plus y square plus z square whole to the power minus 5 by 2 into 2x, that's the inner derivative, plus this function x square plus y square plus z square whole power minus 3 by 2 times of dou by dou x of this x is 1. So if you simplify this, you can observe something, 2 and 2 gets cancelled, of course. Okay, then you would get, if you take minus is outside anyhow, from this term and this term, if you take x square plus y square plus z square whole power minus 3 by 2, so if you take this out, then you would get, okay, it's a minus 3 by 2, so x into x square plus y square plus z square whole power x, and there is one more x, so total x square actually. Okay, whole power minus 1, because this minus 3 by 2 you have taken common, plus this x square plus 1, of course. Okay, so here you would have got only 1, of course. So now you can understand something. This is sorry, there is a minus sign here, one more minus sign, so minus 3x square. Okay, so this is minus 3, so this minus 3 is also constant, that is there, so minus 3 x into x, so minus 3x square multiplied with this whole power minus 1 plus 1 is what you get. Now if you simplify this, you would get minus x square plus y square plus z square whole power minus 3 by 2 times of, if you take LCM, because you can write this as minus 3x square by x square plus y square plus z square plus 1 is what you can write actually. So if you would have written this, if you simplify this, then this term would have become, on the numerator it would have become y square plus z square minus 2x square. So this would be the term actually. Okay, so dou square f by dou x square term would be this. Similarly, if you calculate dou square f by dou y square, similarly dou square f by dou y square is equal to minus of x square plus y square plus z square times x square plus z square minus 2y square divided by x square plus y square plus z square. This is what you would have got actually here, minus 3 by 2 on the top. Similarly, dou square f by dou z square. So if you add, you will get some expression again, which is this constant, and this denominator will be same, and numerator would be x square plus y square minus 2z square. So if you add all these things, dou square f by dou x square plus dou square f by dou y square plus dou square f by dou z square, this would have been 0 actually here. Okay, so this term would have been 0 actually, and this total summation would be 0 in this. Okay, it would have been 0. Normally here you can see the size of the calculation is slightly lengthy, but once you did vector calculus, okay, in fact in vector calculus we come across this is normally called the Laplace equation, okay, and this is f is basically a scalar function which is root of x square plus y square plus z square, so which is 1 by r. So this is the function actually. If r is a position vector, just I'll give you some basics, maybe you can get it. See, r is the position vector which is xi plus yj plus zk. Okay, since anyhow we'll deal this in detail when we talk about vector calculus, but to solve this question you can solve it easily using vector calculus. Look, so if you take modulus of r, this becomes root of x square plus y square plus z square. So let's say if you have a scalar function f of xyz which is equal to 1 by r actually, okay, then what is the value of del square f? This is what need, okay. So del square f, which is Laplacian. How to know which terms are changing? Because you can see this term is a constant, okay. So similarly this is also x square plus y square plus z square, but here when you have differentiated with respect to x y's, this term in the numerator became y square plus z square minus 2x square, okay. Similarly here it becomes, when you are differentiating with respect to y twice, it becomes x square plus z square minus 2y square, because when you have differentiated with x you ended up with minus 2x square. Similarly here minus 2y square, similarly here minus 2z square, and the summation leads to 0 of course, okay, fine. So let's see, in this case the Laplacian of this is actually 0. We can show this. Many of you might have at least seen Laplacian operator which is in Cartesian, at least dou square by dou x square plus dou square by dou y square plus dou square by dou z square is what you get, okay. Since if you have some prior background of vector calculus, I'm just using that background, and this Laplacian can be written as, normally in general convention, let's say if there is some function f which is operated on this, okay, like this. So this Laplacian of f can be written as divergence of gradient of f actually, okay. And when you have these two functions, out of which one is this vector point function and this is the scalar point function, then you can see this f is equal to 1 by r. So if you write divergence of gradient of 1 by r actually here, okay. So when you write this 1 by r, gradient of 1 by r, this gradient of 1 by r will give a vector point function for which the curl is 0 and divergence of curl can be 0. So using this property we can show that this vector would be, this scalar, total scalar product would be 0 actually, okay. Or there is also one more property where you can use is divergence of some function, say phi times a bar. If you have this, this is actually phi times divergence of a plus a dot gradient of phi actually here, okay. So this is the scalar function, and del of or gradient of r power n, so where r is this quantity, so if you have power n, actually this value is n into r power n minus 2 into r bar actually, okay. So if you use these properties, you can in the second method or in the third method maybe, so you can calculate the value of del square f to be 0 of course, okay. The only thing here is it's like phi times of a, or basically a bar times phi is basically del of 1 by r. So if you use these properties, you can easily show this del square f is 0, which anyway I will show you when I'm teaching vector calculus again, okay. So right now, since you don't know these concepts of, since I haven't taught you formally, so I'm using this conventional method to show you that this value is 0 actually, okay, fine. But you can make a note, these two are very useful properties actually in vector calculus, okay. Maybe you can take a note. So divergence of some scalar point function times vector is equal to phi times, phi is a scalar point function, so phi times divergence of a, which is again a scalar, so scalar times function is scalar, and this dot product will again give you scalar actually, okay. But we'll see in detail what is gradient, what is divergence, and how these things can be calculated in detail, fine. So this answer is 0 for the time being. So let's check it up. Some of you have entered 0, none of you, okay. Ashwini has entered, Ashwini Kumar Baiswal, 22 seconds, fine. So let's see, I'll give you one more question before I move forward. Calculate this single choice, and let's say I'll give you some 120 seconds. So calculate this question. F of x is ax square plus by square by xy. A and b are constants. If dou f by dou x is same as dou f by dou y at x equal to 1 and y equal to 2, means at this point 1 comma 2, this dou f by dou x and dou f by dou y is same, then what would be the relation between a and b? Come on, do this question. ABCDs. Okay, you can mark the pole. B, A equal to B by 2, maybe. Even I have to calculate, okay? I don't know the answer, we have to do calculation. This is a PYQ, actually I have borrowed it from PYQ book. Come on, quick, a bit faster. Okay, so chalo. Let's solve this question then. Solution. Given f of x comma y is equal to ax square plus by square by xy. Okay. So normally if you want to differentiate this with respect to x and y partially, you have to apply u by v and all. So it would be slightly lengthy. So what I can do is f of x by y, x comma y is equal to, I can write this as two separate terms, ax square by xy, which gives you ax by y plus by x. So this is what you get, obviously, right? So what is fx then in such case? Dou f, therefore dou f by dou x. So if you differentiate this partially with respect to x, a by y is a constant in the first term and the derivative with respect to x is 1, plus by is a constant, derivative of 1 by x is minus 1 by x square, of course. Now if you want this derivative at the point 1 comma 2, just substitute x equal to 1 and y equal to 2 in this complete term actually. Okay, so if you replace x equal to 1 and y equal to 2, this is a by 2, then plus or minus b into y, so 2b is what you get by 1, that's all. Okay, so a by 2 minus 2b. Similarly, if you calculate dou f by dou y, what is the value of dou f by dou y? Let's calculate again. So with respect to y, if you are differentiating, minus ax by y square plus b by x is what you have. Okay, so if you calculate this value at 1 comma 2, again this function at 1 comma 2, so this is equal to, so if you put x equal to 1 and y equal to 2, this is minus a by 4, minus a by 4. Okay, so minus a by 4 plus b, of course, so plus b. If you equate these two, let's see what happens. So they told these two are equal, so this implies a by 2 minus 2b is equal to minus a by 4 plus b. Now if you bring this a by 4 to the left hand side and 2b to the right hand side, we have 3a by 4 is equal to 3b actually here. Okay, so 3a by 4 is, because a by 2 plus a by 4 gives you 3a by 4, and if you send this 2b to the other side, it is 3b. So if you cancel this 3 and 3, you have a is equal to 4 times of b actually. Okay, so a is 4 times of b, which is in option D actually. Okay, you all got b. How come? A equal to b by 2. Did you make this equal to 0? In such case also you should get a equal to 2b, right? Yeah, a equal to 4b is the actual answer in this case, correct? Because the calculations and simplifications is fine. A into x by y plus b into y by x, 2. So differentiating with respect to x, a by y plus minus b by x square, 2. So when you put x equal to 1, y equal to 2, this is a by 2 minus b, this is correct, minus ax by y square, correct, plus b by x. Okay, 2. When you put x equal to 1, minus a by 4 plus b, then this is also correct. If you equate these two, 3a by 4 equal to 3b. Yeah, I think this is 2. Okay, a equal to 4b is the correct answer. What made you think that b is the correct answer? Any one of you? Because many of you have done the same mistake. Okay, so I want to know what is the mistake. I can maybe clarify it. Come on, please tell me. A equal to 4b is the actual answer in this case. AB equal to 4. AB equal to 4. Where is that? A equal to 4B is the actual answer, right? Yeah, equal to 4 times B. Okay. So I hope this is clear. Is this okay to all of you? Yeah, A by B equal to 4. So obviously A equal to 4B. Correct. Okay. That's option D. Is this question clear to each and everyone? Please type in the chat box. So Sanjay, Sujay, 7 stars, Ram, Gaming, Shiva, Shravan, Icon, Rajna. Read only these names. All. When one student says others copy, oh my god, that should not be there. Yeah, GATE exam, it's not possible. Okay, fine. So A equal to 4B is the actual answer. So the correct option is D actually. So let's see if some of you have marked. None. All of you are with B. This is one very good question. Again, please solve. I'll give you time. Single choice and 150 seconds I'll give you this time. Okay. So think a bit and try to get this answer. Consider two functions where x is psi ln phi and y is phi ln psi. Then which of the following is the correct expression for dou psi by dou x? Okay. Do this question. It's a nice question, a really nice question. You have to think a bit to get this. So psi is a constant, na? Psi. Okay, psi. Okay, fine. Sorry. This psi is actually a function. That's why they are asking, right? Dou psi by dou x. Psi is not a constant. Okay. Psi is a constant. Good. Okay. Think a bit and solve this question. It's a nice question actually, if you think. D, maybe. D. Okay. So currently there's a fight between C and D. Others should give majority now. One of these. Come up with a new party, that's also a C. Hello. The poll is ending up. Fine. Let's see. Solution. Let's try to do something here. Let's check it up. Given x is equal to psi ln phi, given x is equal to psi ln phi and y is equal to something they have given. What is that? Phi ln psi. So this is phi times ln. Okay, as far as I remember, this is a question in 2019. As far as I remember, I'm not sure, but that's somewhere I think. So first of all, you want to calculate psi x. Okay, good. So your aim is to calculate what is this value, psi x. Okay, dou psi by dou x anyway. But clearly this psi is connected with x and y as well. Okay, so first of all, if you want to get psi x, let's do one thing. You call this equation 1 maybe, and you call this equation 2. Okay, so since you want dou psi by dou x, differentiate 1 partially with respect to x. 1 partially with respect to x actually. Okay, so if you differentiate this with respect to x partially, you can see dou x by dou x is 1 first function into derivative of second function. So derivative of this function is 1 by phi into dou phi by dou x, because that I can writing it as phi x. Okay, because this phi is also again some function depending on x and y. So dou phi by dou x plus second function into first function, which is phi x. Okay, so this is the term what that you have. But here you cannot directly declare that this psi x is equal to, so psi x is equal to minus, so let's say psi x is equal to minus 1 by ln phi times plus phi by psi multiplied with this phi x. Okay, so this is the equation that we have, correct? If you differentiate this with respect to x partially, this is what you will get. But in this case there is one issue. This phi with respect to x and phi is there, psi is also there. This y is also connected with phi and psi. Okay, so means in this expression there is indirectly there is involvement of y actually. Okay, but in the given options clearly the options are only functions of phi and psi, of course. Okay, so let's see, and most importantly in all options you have ln psi. Okay, but if you look at this case there is no ln psi term. Okay, so let us try to get the ln psi term. So where is ln psi? Here. Okay, but you want to take advantage of this ln psi term, but at the same time you don't want to have y term. So what I can do is, we can think something creative and we can do this, differentiating 2 partially with respect to x, partially with respect to x. So this implies dou y by dou x is equal to dou by dou x of phi times ln psi. Okay, because in the options there is involvement of ln psi and I can get ln psi only from this equation, but at the same time there is no y in the options, so I have to eliminate y. So which makes me to differentiate with respect to x partially. So can someone tell me, if this is y and if I am differentiating with respect to x and these two are two implicit functions, functions which are separately defined, so this value is 0 straight away. Okay, because x is a separate function and y is a separate function, so ln dou y by dou x is 0. So this implies phi 0 is equal to phi times derivative of this 1 by psi times psi x plus second function times dou phi by dou x, which is phi x, of course. Okay, and in this option there is nowhere phi x, so we can eliminate this phi x actually. So let's do that. What is the expression for phi x actually? Okay, so phi x is equal to, so phi x is equal to minus phi by psi times psi x, this whole term, into 1 by ln phi. That's what you get. Okay, so because that's what you can do, this phi x is equal to minus of this combination divided by ln psi. Now from these two equations what I can do is, since phi x is not there in the options, so we can replace this phi x to the in this equation. Okay, so bring this phi x and put it in this equation. So this tells you psi x is equal to minus 1 by ln phi minus 1 by ln phi. I think this is multiplication, right? Sorry, this is multiplication, huh? Minus 1 by, so just see, no, here something I have made mistake, I think. Just a second. 1 is there on the left hand side, so 1 minus, or 1 by ln phi times of 1 minus psi by phi into phi x, correct? Okay, so now I am replacing this because this phi x is there, this 1 is there always on this left hand side. So if you replace this phi x value here, minus no, there is no minus now, 1 by ln psi ln phi actually, so 1 by ln phi into 1 minus this psi by phi is as usual into this phi x. So phi x you replace again here, so phi x you replace with this value, so which is minus phi by psi into psi x into 1 by ln psi is what you get. Okay, so this is the value. Then if you simplify this, then minus of minus plus, then psi and phi gets cancelled, of course. So you have something like psi x is equal to 1 by ln phi times of, then 1 plus you have psi x in the numerator, so psi x by ln psi. So that's it. Okay, so now everything is only in terms of psi x and only ln phi and ln psi terms are there. So let's calculate the value of psi x from this function. Let's say if you multiply this ln phi here, so ln phi times psi x into, if you take LCM you will get ln psi also here. So this is equal to ln psi plus psi x, ln psi plus psi x. So what is the value of psi x from this? So psi x is equal to ln psi divided by ln psi divided by ln phi ln psi ln phi ln psi minus 1. That's the value actually. Okay, so it's a bit of thought you have to do here, because why I am doing this is, first of all, who told me to do this process is, first thing, you need psi x, okay, which you'll get here if you differentiate this partially with respect to x, okay. At the same time, the final options, there is involvement of ln psi, okay. So how do you get ln psi? You have to use this equation, but you have to get rid of this y. So if you have to get rid of this y, ultimately differentiate it with respect to x, then that term will be 0. So just put the expression of phi x from here and simplify, you will get the actual answer. So let's see if this is in one of the options. Ln psi, so x is not there, actually this is part is wrong, so x is actually not there, x is not there. So ln phi, what is the value you have? Ln psi actually, okay. So this is wrong. So ln psi by ln phi ln psi minus 1, ln phi ln psi minus 1, yeah, this is correct option then, okay. So D is the actual correct option in this case. The technique here is to use this to, in the final options you have ln psi, to get ln psi you have to use this, but you don't want to have y in this, so differentiate this with respect to x partially, okay. Then substitute this and simplify, you'll get the answer. Clear? Is this question fine to all of you? I'm not sure about the branch, but I think this question came in 2019, okay. Fine. So this is the value for psi x from this equation. So is this question clear to each and every one of you? Yes or no? Please type it in the chat box. Okay. So D is the actual answer. So I think, let's see if some of you had any thought to do this. Vijay has answered. Okay, good. 2 minutes 5 seconds. Okay. So let's. Okay. So before we go for further things, let's start this partial derivatives and Euler's theorem. Okay. So right now we have seen enough knowledge in partial calculation of partial derivatives. The first thing I would like to give is homogeneous functions. Homogeneous functions. Okay. Homogeneous functions actually. So what is a homogeneous function actually? A function f of x comma y in general, or in general of any variables, but let's say if we are dealing in 3 variables, so a function f of x comma y that is equal to f of x comma y is said to be homogeneous, is said to be a homogeneous function, is said to be a homogeneous function if for some scalar k, for some scalar k, f of x kx comma ky can be written as some k power n times of f of x comma y, okay, and n is known as degree of the homogeneous function, which is very important when we define Euler's theorem. So degree of homogeneous function, okay. So this n is basically called the degree of the homogeneous function, and you can check if this is the degree of the homogeneous function, n is the degree of homogeneous function. Like example, f of x comma y, if you take it, it's like x cube plus 3x square y plus y cube. Let's say if I take this function, okay, then ultimately in this function, if I replace x with kx and y with ky, so this implies f of kx comma ky is equal to kx whole cube plus 3 times kx whole square into ky plus ky whole cube actually here. So if you simplify this, if you take k cube common, you'll get x cube plus 3x square y plus y cube, which is again k cube times f of x comma y. So you can have functions like this where if you replace x with kx and y with ky, you can pull out a k power n constant from the result, and you can show this the function is of this form, okay. So in such case, it is something like 3, okay. So this k equal to 3 is the degree of homogeneity, okay. So this 3 here, so you can say this is a homogeneous function, a homogeneous function of third degree, okay. So this is a homogeneous function of third degree is what we have here, okay. Sorry, hi sir, I'm a village from, I've been following electric classmates. Okay, thank you. Yeah, just continue learning, okay. So this is third degree, fine. So what is the advantage of these functions? That's the main question. Let me ask you one question. For f of x comma y is equal to x cube plus, what is this? We have 3x square y plus y cube, okay. So let's say this, if you calculate, find x into dou f by dou x plus y into dou f by dou y. So if you do this, let's say if I ask you to calculate this, okay? In matrix, if I said 0, the function are homogeneous. It's homogeneous system of equations, okay? That's a different story. Ax is equal to 0. That is called homogeneous system of equations. Okay, so here I'm just defining the homogeneous functions actually, okay? So let's see. If you calculate this, then let's see what happens. I'm just doing it a bit quick. You can get it. X cube plus 3x square y plus y cube. So this implies fx, partial derivative with respect to x, is 3x square plus 6xy, and fy is equal to 3x square plus 3y square. Okay, so you have this. So ultimately, if you using this, if you compute x into fx plus y into fy, okay, this is just anyone can do this partial differentiation. Just follow quickly. You can get this. So x times of what is fx? 3x square plus 6xy, of course, okay, plus y into fy. Fy is 3x square plus 3y square. So if you simplify this, you can see 3x into x square, 3x cube plus 6x square y plus 3x square y plus 3y cube. Okay, so which means you can see you got some result which is okay. So if you take this as common, 3x cube plus 9x square y plus 3y cube. Okay, you got this result. Fine, good. So let's see if I give you one more example. If f of x comma y is equal to x square plus y square by x minus y, let's say, okay, or x plus y, let's say x plus y, you take this. Then if I ask you x into dou f by dou x plus y into dou f by dou y actually, okay, so dou f by dou y. If I ask you this, then ultimately, you know, the calculation of this fx, partial derivative with respect to x, and fy, partial derivative with respect to y, is not very easy as I have done in this case. In this case, it's very easy because it's a straight function, you have differentiated. But here, if you try to differentiate, it takes some time actually, okay, because you have to apply u by v rule, then simplify all these things. But if you, okay, I'll do it because I want to show you something. Let's calculate f of x comma y is equal to x square plus y square by x plus y actually, okay. Let's make the life complicated a bit. Okay, so then let's calculate fx. So if you calculate partial derivative with respect to x, so it's a ratio of two functions first of all. So denominator function into derivative of this numerator function, which is 3x square, minus the numerator function into derivative of denominator with respect to x partially, which is 1, this term divided by x plus y whole square. Okay, so this is the partial derivative. So if you simplify this, let's see, 3x square into x, 3x cube minus x cube. So you have 2x cube plus 3x square y minus y cube. Okay, so you divided by x plus y whole square actually here. Okay, so this is divided by x plus y whole square. Then let's see fy. If you calculate fy, x plus y 3y square minus x cube plus y cube times 1 by x plus y whole square. Okay, so if you simplify this again, you would get 3xy square, 3xy square actually, so 3xy square plus 3 cube minus 3y cube minus y cube, 2y cube actually, because there is 1 minus y cube, so 2y cube minus x cube by x plus y whole square. Okay, so you got this. Now let's calculate, let's substitute this fx and fy in these terms, and let's try to simplify this. Okay, I know it's a hectic process, but I just want you to do once. So calculating x times fx plus y times fy actually here. Okay, so if you do this calculation, let's see, if you multiply x on the top, 2x power 4 plus 3x cube y, 3x cube y of course, minus x y cube. Since denominator is same in both the cases, I'll add up the common denominator, plus y into this term gives 3xy power 4, no, 3xy cube 3xy cube plus 2y power 4 minus x cube y. Okay, so this is the term I have. So this complete term divided with x plus y whole square actually. Okay, so this complete term divided with x plus y whole square. So let's see if I simplify this. 2x power 4, 2y power 4, these things are quite common. 3x cube y and x cube y. So I can cancel this and make this 3 2. Okay, similarly I can cancel this and make this 3 a 2 of course. Okay, so if I make this 2, then let's see, this page is not sufficient. X into fx plus y times fy is equal to so if you take a 2 common, look what you can have of course. Okay, so this is x power 4 and this is x cube y actually. Okay, and this is xy cube and y power 4. From these two terms, if I take x cube common, so 2x cube, if I take common, I have x and a y here, so x plus y. Then from this term and this term, if I take y cube common, 2y cube common of course, I again get x plus y divided by x square, x plus y whole square. That's what we have of course. Okay, so x plus y whole square. So now you can cancel one common factor, x plus y is square, and these two terms gets cancelled. So you figured out something like x cube plus y cube by x plus y actually here. Okay, so we have done a lot of procedure, in fact a lot of some hectic calculation in between to achieve this result. Okay, but this Euler has given one very favorable. Okay, so please give sufficient time for writing. Okay, I'm also writing, right? Okay, but I understand your writing short notes takes a bit of more time. It's okay, but in general if you check it, this function whatever you get here, can I write this as 2 times f of x comma y actually, what I got here, because this is my function and at the end I have got the same function of course. So 2 times of f of x comma y, correct? Can I write this? Yes or no? So you had done some calculations, you have calculated partial derivative with respect to x, partial derivative with respect to y, you have substituted and simplified, juggled the terms, you got this answer. But if you know Euler's theorem, you would have told that by the moment I have given you this expression, you would have told directly the answer is going to be 2 times of f. Okay, you would have directly told this. Let's see how to do that. Okay, just a minute, I'll have water. Are you all understanding these things? Come on, quickly type in the chat box. Yeah, can you all get these things? Yes or no? Please type it in the chat box. Now let's see what is an Euler's theorem is. Okay, you know what is a homogeneous function now. What is this result? So let's see what is an Euler's theorem actually. Let's write it up. Euler's theorem. So this tells you if f of x comma y is a differentiable, of course, as usual, because fx, fy, these things has to exist, and a homogeneous function of degree n. Homogeneous function of degree n actually. Okay, so this is a homogeneous function of degree n. Then point number 1, first point is x times dou f by dou x plus y times dou f by dou y. Okay, so I have written the word differentiable because this partial derivatives has to exist, and if it is a homogeneous function of degree n, this summation is always equal to n times of f actually. Okay, so this summation is always equal to n times of f. The second point is, see, in this case when I have asked you to calculate this, you have to do this much of calculation and finally you got this value as 2f. Okay, let's suppose if I have asked you x square times dou square f by dou x square plus 2xy times dou square f by dou x dou y or dou y dou x, doesn't matter, anyway it's same, plus y square times dou square f by dou y square. Okay, so if I have asked you to calculate this, imagine calculating one more derivative of this with respect to x. It's very it's not complicated, it's easy, but it's very lengthy. Okay, similarly here it would have been lengthy actually. So but this value is actually equal to n times of n minus 1 into f actually. Okay, so that's what you can get. This is n times of f, that's n into n minus 1 times of f, like which I can show you with a simple example. For example, consider this example. Okay, so f of x comma y is this term. I have calculated x into fx plus y into fy, and you know this is every term is of third degree. This is degree 3, 2 plus 1. This is again third degree. This is also third degree. So this is a third degree homogeneous function actually. Okay, so that's why when you have calculated this x into fx plus y into fy, if you take 3 common from these terms, if you take 3 common, then you have x cube plus 3x square y plus y cube, of course. Okay, then in such case this value is f, whatever I have given you, this function. Okay, so it's 3 times of f because of this thing. Then since it's easy, I'll show you in this case. Let's see, this is a homogeneous function, so this implies x square fxx plus 2xy fxy or fyx, anything is fine, y square times fyy is equal to, as per the Euler's theorem that you know now, 3 into 3 minus 1, 2 times of f, which means you should have got 6 times of f, which means this expression, if you calculate, the answer would be 6 times of x cube plus 3x square y plus y cube. This would have been your answer. Okay, so let's check whether you are getting that answer or not. If you differentiate this with respect to x, once again, fxx is equal to, differentiation of this term is 6x plus, when you differentiate with respect to x, treating all others constant, it is 6y. fxy, so what is fxy? Dou by dou x of dou f by dou y. So you already have dou f by dou y, differentiate this with respect to x partially, so this is 6x. Okay, or if you have differentiated this with respect to y partially, you would have got 6x again. Okay, and fyy, so what is fyy? Which is 6y, of course. Okay, so which is 6y. So let's calculate then. X square times fxx plus 2xy times fxy plus y square times fyy. Okay, so if I calculate these terms, let's see, x square times of this, which gives you 6x cube plus 6x square y. Okay, so that is the first term. Then 2xy times fxy, so 2xy into 6x gives you 12x square y plus y square times fyy, so y square into this gives you 6y cube. So this is 6 plus 12, 18. So if you take a x common, a 6 common, you would have got this expression again. Okay, so since this is a simple example, you are able to calculate fxx, fyy, fxy. But if you go for this example, calculation of fxx, fyy, these things are much calculative, a very lengthy calculations would come over. But this theorem or Euler's theorem will actually help you in getting out of those situations. Fine? Did you all understand this? Yes or no? Okay. So every one of you, please type it in the chat box. Is this fine and clear to each and everyone? Did you all understand the effect or the use of this theorem? Okay. Everyone, all of you, type it in the chat box. Hello. Let's see one more case. If f of u is homogeneous, function of degree n, actually here, then point number 1, x into dou u by dou x plus y into dou u by dou y is equal to dou u by dou y is equal to n times of f of u by f dash of u actually. Okay, so this is one function actually. Again, I can show you the reason easily. Sometimes what happens, let's say if I give you this is equal to x cube plus y cube by x plus y, like the same example I have taken. So u is, instead of f I am writing u, so u is a function of x and y. So clearly this is homogeneous function. So if I have asked you this in this case, you would have told n into basically 2 times of u. Okay, x into dou u by dou x plus y into dou u by dou y would have given you 2 times of u. Okay, but let's see if I put sine inverse of this, okay, sine inverse of, or maybe some function, so that sine inverse of this function, then ultimately calculating dou u by dou x and dou u by dou y means when u is this function, calculating this quantity is very lengthy. Yes or no? Because individually identifying dou u by dou x and dou u by dou y terms is very calculative in this case of example. Okay, so what we can do is, sometimes this function directly is not homogeneous. This is not a homogeneous function, okay, because if you put kx and ky here, you cannot take k square outside of this sine inverse. Clear? You cannot take k square outside of the sine inverse. So this function is not homogeneous. But you can do one thing. You can define a function sine u which tells you x cube plus y cube by x plus y. And this u itself is not homogeneous, but this sine u is homogeneous actually. Okay, so that's how some function of u, here it is sine u, maybe cos u, tan u, whatever. So this function is homogeneous. If that function is homogeneous, then this calculation is actually equal to n times that f of u by f dash of u. Look, I would like to tell you one thing. So see here, observe carefully one thing here. If f of u is homogeneous function, of degree n, let's say, okay, this is homogeneous function of degree n, then as per your Euler's theorem, you should know x into dou by dou x of f of u plus y into dou by dou y of f of u. This should be equal to n times f of u. Yes or no? Please type it in the chat box. Can I write this? If this function f of u is homogeneous, as per Euler's theorem, you can write this point, correct? Because this f of u is homogeneous, so x into dou by dou x of this plus y into dou by dou y of this is equal to n times of f of u. Can I write this? Everyone, please type it in the chat box. Quick, a bit faster. Do it. Okay. Now, what can I do is, look, I can differentiate this x into dou by dou x of this function. So derivative of a function is first of all f dash of u into this u is again depending on x, so ultimately dou u by dou x, the inner derivative of the function, plus y into dou by dou y of this function is f dash of u into the inner derivative, which is dou u by dou y, n times of f of u occurs. Okay, now from these two terms you can pick this f dash of u common. So if you pick this f dash of u common, then you have x into dou u by dou x plus y into dou u by dou y is equal to n times f of u, obviously. So if you delete this here, then you would get here. That's all. Okay, so this is the function. That's why I have given you this result. Okay, now in such case, if I ask you, fine. Okay, so let's see. In this case, if I ask you, this is a homogeneous function of second degree actually. So if I ask you x into dou u by dou x plus y into dou u by dou y, you could tell easily it's 2 times, because it's second degree, f of u sin u. So derivative of sin u is cos u. That's it. So 2 times of tan u actually here. So that's a function. Okay, now you can ask me what is tan u now. That could be one more question. Actually, if this is sin u, you take a triangle, you take this side to be x cube, not this side, sorry, x cube plus y cube, and you take this side to be x plus y, then you calculate this side. Obviously you can calculate using Pythagoras theorem, then you can write what is tan u in terms of x and y if you want. Okay, it's not a big question, but doing this is very simple rather than following the classical procedure. Fine. And sometimes this is referred as capital F of u. Okay, is this fine to every one of you? Please type it in the chat box. Is this okay? So 2 tan u is homogeneous. This function need not be homogeneous. Okay, it need not be, but in this case it is actually. Okay, because the reason is, if u is a homogeneous, u is non homogeneous, right? Yeah, then need not be. In such case it need not be. Fine. Let's see one second case, which I'll just give the formula again, showing it would be very lengthy. So in such case, if this is the case, if f of u is homogeneous, the second point is x square times dou square u by dou x square plus 2xy dou square u by dou x dou y plus y square times of dou square u by dou y square. So this is equal to f dash of u times of f of u minus 1. Okay, so this I'm not showing as of now because these calculations and all would be slightly lengthy. The procedure is energy tag matters in life and society? Very nice question actually. So it definitely gives a tag basically in your interviews or in your profession, but I think society and life maybe. Okay, I don't think much, to be frank, but it's good to have an NIT tag in your profession, 100%, which means in your life. Okay, and 90% of the times in your life, don't bother what society tells you. Okay, whatever you do, it tells something, okay, against you, not in favor of you. Fine. So well, NITN speaks. Okay, good. So yeah, I would like to give one example again. Anyway, not for this. This is the point which concludes. Let's see if u is equal to f of x comma y plus g of x comma y plus h of x comma y. Okay, so plus h of x comma y. See, one thing I want to tell you is, guys, let's anyway, every day I teach only concepts. Today I'll teach something different actually. If you are from IIT or NIT or IISc, from or MIT, doesn't matter, any place, whatever the place you might be, until and unless you have knowledge, you cannot survive. Okay, being an NITian or being an IITian, being an IIScian or any other institute will create your first platform. That's it. Okay, so when you say people, when you go and say that I'm from NIT, and let's say for example I'm from Tier 3 college, then definitely people give that one step above for you. Okay, but once you join the things, let's say if you start a job or if you do anything, once you join, only your performance is what it matters. Okay, there are many people who did very excellent from Tier 3 colleges and Tier 2 colleges, but people who got graduated from this Tier 1 like NITs, IITs and all, there are many people again who didn't do very well. Okay, so it all matters in you. Clear? It depends on the performance, how you perform once you join the things. Okay, maybe as an NITian or IITian, you may get the first step. Okay, but after that it's purely your knowledge levels and your things which you should. Okay, you're in Jabalpur Engineering College, good. Place doesn't matter nowadays. Okay, in fact guys, I'll tell you one thing very honestly, very frank, to be very frank. Okay, nowadays people write JEE Advanced. Okay, which if some of your brothers or sisters are doing, younger ones are about to do this, just tell them. Okay, in life if you don't get IIT, if you don't get NIT, there's no need to get very depressed. Okay, to be frank, I've seen people, okay, they motivate highly to join IITs and NITs for BTech, and if they don't get it, they undergo depression, a lot of things. Okay, because their age was also very small by the end of their +2, it's almost like 17-18 years or 19 hardly, so it's slightly difficult for them to battle. But nowadays everything is available for free. Okay, the only thing is you have to use your time very efficiently, and you have to basically take good use of the resources. That's all. Okay, everything is available. Do you think I've been teaching you so much maths? Do you think all this maths is invented by me? No, right? 100% no. Okay, not even a single point is invented. Maybe some few teaching, the way of teaching, all these things were I have modified a little bit, but the content, purely 100% of the content is got or borrowed or copied from somewhere. Okay, like textbooks, authors, we have a lot of place. Okay, so to be frank, like whatever the research we are doing, in fact, if we display that, you won't understand, to be frank, honestly. Yes or no? Let's say if I write one equation, something like if I write something, obviously you won't understand. Okay, and it doesn't matter whether I write this or not, you won't get it. Okay, and whatever the things I am telling, let's say for example if I teach you 2 + 3 = 5, Now I cannot claim that I invented this just before this class I'm teaching you. It's been there since thousands of years back, right? And so the idea here is everything is available. So the only thing you have to do is take advantage of this time resources which are available and try to excel in life. Got it? It all matters is what's the stuff in your mind, not the tag. Tag is just for the first step. After that, only the stuff in your mind takes you to heights. Okay. Hello. So if you have these things, if u of x comma y is f of x comma y plus g of x comma y plus h of x comma y, are where f, g, h are homogeneous functions, of degrees m, n and p respectively, m, n and p respectively, then point number 1 is so x into dou e by dou x plus y into dou u by dou y is equal to x into dou e by dou x plus m into dou e by dou y equal to m times f of x comma y plus n times g of x comma y plus p times h of x comma y actually. Okay, this is again a very simple thing to show. Of course, how we can show this? Like, you know, this term is equal to x into dou by dou x of u is f plus g plus h plus y into dou by dou y of f plus g plus h. Okay, and if you simplify this, you can multiply this x separately because you can split this differentiation at all plus signs. I can write this term as x into dou f by dou x plus x into dou g by dou x plus x into dou h by dou x. Okay, then coming to this, y into dou f by dou y plus y into dou g by dou y plus y into dou h by dou y actually. Then once you can understand this, if you combine this first and the fourth term, okay, so let's say this is the first term and this is the fourth term, x into dou f by dou x plus y into dou f by dou y, this f is a homogeneous function of degree m. So these two summations will lead to m times f actually. Okay, plus this term, or maybe I'll change the color so that you can get this term plus this term gives you n times of g, because if g is a homogeneous function of degree n, x into dou g by dou x plus y into dou g by dou y gives you n times of g plus this term and this term. If you sum up, it gives you p times h, of course. Okay, so that's what you have. Similarly, if I write x square dou square u by dou x square, y square 2x by dou square u by dou x dou y plus y square into dou square u by dou y square, all these things, you would get m into m minus 1 into f plus n into n minus 1 into g plus p into p minus 1 into h, of course. Okay, so this is how we take advantage of the Euler's theorem in many calculations actually. Fine. So let's now move on to Taylor series actually. So let's see. In single variable, I have given you how come the Taylor series exist. So let's see if f of x comma y is continuously differentiable, at the points at the point a comma b, let's say at the point a comma b, then Taylor series expansion then the Taylor series expansion of f of x comma y about the point a comma b, is given by so normally this is the Taylor series expansion is given by f of x plus b. Okay, 2 dimensions, let's down 2 dimensions. F of x comma y is equal to f of a comma b plus f of a comma b plus, what's the difference between Taylor series and Taylor's expansion? Normally this both are same, but normally when you have the plus signs in between, it's called a series more formally. Okay, few people refer to it as expansion, but the more technical term to call it is series actually. Okay, because series is summation of terms. Fine, summation or subtraction, anything, but in general when you connect so many terms by plus or minus signs, algebraic terms, it becomes a series. Okay, so f of a comma b plus, now let's see, 1 by 1 factorial into x minus a times fx at a comma b plus y minus b times fy at a comma b. So this is the first term actually here. Okay, then plus 1 by 2 factorial, let me elaborate this actually, f of x comma y is equal to 1 by 2 factorial times of x minus a whole square into second derivative of f at a comma b plus 2 times x minus a y minus b fxy or fyx, doesn't matter, both give you the same thing, a comma b plus y minus b whole square times fyy of a comma b actually. Okay, so this is what you, similarly plus the third term, 3 factorial term, x minus a whole cube f triple derivative with respect to x is dou cube f by dou x cube at a comma b plus 3 into x minus a whole square y minus b into f, so x square and y, so x and 1 y of course. Okay, at a comma b plus 3 into x minus a times y minus b whole square f, so 1x and 2y terms, so x y of a comma b actually here plus the third term which is y minus b whole cube times f y of a comma b. So this is the 3 factorial term. Similarly you can go with the 4th factorial term, but generally I'm terminating the series here, plus and so on. Okay, so this can actually move up. So this is basically called the Taylor series up. In general, normally you can expand Taylor series in n dimensions. Okay, normally this is a 2D, I mean 2 independent variables. Even if you have n independent variables, you can expand the Taylor series of course. Okay, what does the Laplacian mean in real life? Basically, okay, just let's finish this, I'll go back. Okay, because Laplace equations are very powerful equations which deals with steady state equations. Okay, wave equations, heat equations and all. When we teach partial differential equations, you'll come to know of these points. Which branch are you from? 7 stars, just comment in between. So this is the Taylor series expansion up. Okay, then let's see if you try to model it into single variable. Okay, for single variable, the function is only in terms of x. Okay, there is nothing in terms of y. So if the function is only in terms of x, this implies fy is equal to 0, fxy is equal to 0, because once you start differentiating it partially with respect to y, it becomes 0 actually. Okay, so any involvement fxxy is 0, fxyy, all these things are zeros of course. Wherever there is involvement of y with respect to partial differentiation, it becomes 0 actually here. Okay, so similarly, so therefore you can observe f of x comma y, if you expand it, if you have only f of x for example, okay, there is no involvement of y, you are dealing in single dimension, let's say, then in this sequence you don't have this b, also only a, so f of a plus 1 by 1 factorial into x minus a into fx. Since the function is only with respect to x, you can differentiate it partially with respect to x of course. Okay, so y base of algorithms is always positive. Just a minute, I'll convey you. So x minus a, this term will sustain. So this function is, this fx is actually partial derivative of this f with respect to x. But if this function consists only terms of x, there is no involvement of y, this partial derivative is same as exact derivative. Okay, so therefore f dash of x, f dash of a, okay, at x equal to a, plus then this term, as I told you, this partial derivative with respect to y for a function involving only x is 0, so this term is 0. So you have the term closing like this, plus 1 by 2 factorial into, then again this term will survive because this is only a function of x, and these two are also dou square f by dou x square, which is d square f by dx square here. So 1 by 2 factorial times x minus a whole square times f double dash of a. Then coming to the two terms, here there is involvement of y, so this term would be 0, this also would be 0. So this term ends here. plus 1 by 3 factorial times of, similarly you will have x minus a whole cube f triple dash of a, that term. Okay, and clearly involvement of y, so this term would be 0, this would be 0, this would also be 0 actually. Okay, so and this series will go on actually, so which if you write in a proper form, you will get f of x is f of a plus x minus a times f dash of a by 1 factorial plus x minus a whole square times f double dash of a by 2 factorial plus x minus a whole cube into f triple dash of a by 3 factorial, and so on. This series will exist like this. Okay, so but that's the general. Yeah, I'll tell Sami, just a minute. So this is the 2D and this is a 1D, of course. Okay, 1D you have already seen in single variable calculus, but 2D is this actually. Now coming to your question, why base is always positive? Look, if you take the log function f of x, normally if you have the definition, you have a power x is equal to n, then the definition is given as log n to the base a is equal to x, of course. Okay, then when you have negative powers here, and if in general this n log is defined only for positive numbers, the reason is if you want to be in the real plane, okay, if you want to stay in the real domain, if you don't want to go into the calculus in the complex plane, then this a should be always positive. This a should be always positive, because minus 1 whole power something, so let's say 1 by 3, 1 by 4, all this will lead to complex numbers actually. Okay, so that's why even though if x is positive, but this a being negative will lead to a complex plane. Okay, so like let's say this x, a power x equal to n, so let's say if I take minus 1 whole power 1 by 3, you don't have a real number which satisfies this. Okay, so it's a complex numbers. So that's why if you want to stay in the real plane and define real things, you have to have a to be positive always. Okay, also a cannot be equal to 1. The reason is if you write 1 square equal to 1, 1 cube equal to 1, in all these cases this implies log 1 to the base 1 equal to 2, log 1 to the base 1 is equal to 3, so which is ambiguity again. Okay, so that's why, since because of this you cannot have this a to be 1, and that's why log is not defined for base 1. Fine, clear? Any doubts till this point? No? Okay, so then let's see. Someone asked me what is Laplace equation tells you. In general, when you talk about physical wave equations or heat equations, these things, you generally end up with these terms equal to 0. Means del square u. In 1D it is, I have written only this. So this equations physically tells you when things are not changing with time. Okay, if things are not changing with time, then with respect to the position how things change, that's what it purely gives you. But when you get many times, you know, when you model physical systems, you'll end up with differential equations, which again I'll tell you after this multivariable calculus we'll start differential equations. There you will see many physical systems will finally yield to differential equations actually. Okay, and when you solve the equations, it's very frequent you'll end up with this equation if you make a steady state assumption. Okay, which I'm not doing it as of now, because the idea is to solve the heat equations, wave equations and all, which we will see when we come to partial differential. Fine. In heat transfer, anyone from mechanical, they can get it hopefully. Many of you might have seen this equation, right? Many of you might have seen this equation. Okay, now in this case, when we linearize the system, when this difference x minus a, these things are very, very small. Okay, so let's see in this equation, like for example, let's say if there is no heat generation, and if you make steady state assumption, you will again end up with, which is a Laplace equation, and ultimately temperature is linear function of x. Okay, these things all you might seen. So these are many examples where you end up with Laplace equation. Okay, in fluid mechanics, del square phi, velocity potentials, electric potential also, you can see del square phi for a conservative field, electric field is 0, where phi is the electrostatic potential. You might have seen this. Okay, there is an analogy between fluid flow and current flow. At times people come across all this. Okay, so this is basically the Taylor series actually. Okay, the Taylor series expansion is this. So let's see anything that we here. Okay, so the idea is basically in general, so differential equations differentiation equations are non-linear, isn't it? No, it can be linear as well. Like the equation what I have written now is a linear equation actually. Okay, there's no non-linearity here. In fact, if you see, normally if you try to analyze any fluid flows and all, you will have an equation like this. Laplacian of a vector is equal to rho times dv by dt, which is, if you expand slightly, v by t plus v dot del operating on. Okay, so this is a normal fluid flow equation, one of the standard equation actually. So in this case, it's nonlinear partial differential equation because of this product. So differential equations can be linear and nonlinear as well. Okay, fine. So is this clear to each and everyone? So please type it in the chat box. Okay, so did you understand how you generate a Taylor series for two variables, and from this two variable Taylor series, how can I deduct the single variable Taylor series? Okay, in general, I'll just give you some point out of interest. This is in 2 dimensions. Okay, means two. I mean, this is in single variable, but this is in 2 dimensions actually. Okay, in 2 variable, it means if you have 2 independent variables. In general, if you have n dimensional space, we write this as f of x bar vector plus some vector p is equal to f of x plus, you will write this as the gradient Hessians and all. Okay, so basically there is a matrix which is called, if some of you are from electrical, you might have heard it very easily. Otherwise, others generally learn it in something called optimization. Okay, not in single variable optimization, again in multi-variable optimization. Okay, when your function is depending upon, let's say, more than 2 or 2 variables, we take the advantage of this Hessian actually, which I'll generally show you maybe using some optimization. General Taylor series expansion in n variables. Expansion, general Taylor series expansion in n variables. Normally in any optimization books you have this, okay, which I can show you, but I'm not opening textbooks because this is an open source. I cannot do that. So in general, maybe I'll look some images which you can get. All these are single variable, double variable. That's it. Just a second. Maybe you can have this in terms of 3 variables. Yeah, this is in terms of 3, but yeah, this is the case. There you can see. This is the summation. This can also be written in vector form, which we will see later maybe here. Okay, I think this is a direct thing from Wikipedia. You can just open. So you can see all this is basic stuff, single variable, double variable, all this. But if you in general try to generate n variable, then it turns out to be not given somewhere in, right? Yeah, here it is. Taylor series in n variables in general. Okay, so this is the expansion, general expansion. Right, guys? Yes, fine, it's okay. I hope you can see this. So this is the general Taylor series expansion, but this can be easily written in terms of vector form, and we get across certain matrix called Hessian matrix. Complex, it's not a complex matrix, it's a real matrix actually. Okay, so if you can open any optimization book. Normally I generally use this in my studies, but if you open, I'd like to suggest one book, numerical optimization. In fact, any optimization book you can open when you have the gradient descent methods, all these things, optimization by numerical optimization by, what is this name? Sheldon knows. Just a second, we can get it. Numerical optimization. Just a minute, I'll give you the author name so that you can see. Numerical optimization. Yeah, this is the book. Optimization by Stephen J. Wright. Yeah, correct. So this is by Stephen J. Wright. Correct. So this is the book. You open this, you have the general Taylor series expansion for n variables. You can study, you can understand, but you should have some idea of vectors and all. So it connects vectors, matrices, Hessian matrix and all in order to generate this in n dimensions in a general form. Okay, so that's the idea. But anyway, in gate examination syllabus, that too in for mechanical and few people, you have 2 variables. Otherwise, you have only single variable. Fine. See, homogeneity is different in different senses. Okay, like let's say if you talk about materials. Okay, in materials we call the property a property to be homogeneous if it's not changing with with length, or basically if you move in a particular direction. Okay, isotopic and homogeneous, these are 2 important assumptions which people made. homogeneous is something which changes its sense from things to things. Okay, so in case of materials, it's talked about properties. In case of homogeneity is having no change. Okay, so it's like for example, in the equations what you have to, every term has third degree. Okay, like for example, you see in this example, every term is of third degree, so it's like the same nature in all this case. Okay, weak in maths, what should I do? Just start learning. Okay, maybe you are weak today but won't be tomorrow. Okay, so just start learning and keep acquiring knowledge. Fine. Okay, so I think there's no time today to start maxima and minima. It's okay, we'll start tomorrow, no issue. Constrained and unconstrained maxima and minima, and also I'll give a bit of introduction to, yeah, of course, in constraint maxima and minima we'll talk about Lagrange's multipliers. Okay, so maybe we'll wind up for today because the time is up and maxima and minima concept time would not be sufficient. Okay, since I have not taught this, questions we'll do tomorrow. Okay, because since I haven't taught you that, you cannot do those. Anyway, in tomorrow's class we'll do. So in today's class, basically the idea is about homogeneous functions. Then we talked about the Euler's theorem, and we have also talked about what else we did talk? Taylor series in 2D. Taylor series of f of x comma y. Okay, so at a given point, of course. So these are the things which we have covered actually in today's class. So in tomorrow's class, we'll again look at the concepts of maxima and minima, both constrained and unconstrained maxima and minima. We'll look at some nice points called the saddle points, all these things. So don't miss the session. Okay, and again we'll meet at 7 p.m. of course with this continuation. Thank you for today. Okay, because only hardly 4 or 5 minutes is left, so even if we start, we couldn't make it. Okay, so fine then. Any doubts do you have? Are you all understanding all these things? Look, this triangle thing, what I have done is here, when this function is given in terms of x comma y, people want to write the final answer in terms of x comma y. Okay, but you have tan u. Okay, then how to write this, convert this tan u into x comma y? You know sin u equal to this, then ultimately sin u is equal to this, implies if this angle is u, then sin u tells you x cube plus y cube by x plus y. So ultimately if you apply Pythagoras theorem, you can calculate x plus y whole square minus this under root gives you the value of this side. Okay, so then you can write tan u, x cube plus y cube by this expression in terms of x. So if you replace that, the final answer would be in terms of x comma y. That's it. Okay, because when question is given in terms of x comma y, generally people expect to write the answer to be in terms of x comma y. Okay, so that's I have explained you. Clear? Okay. So thank you all then. We'll meet tomorrow again at 7 p.m. and we'll talk about maxima and minima. Okay. Any doubts? Or is everything fine? Okay then. So thank you all. Good night. Take care. We'll meet tomorrow at 7 p.m. sharp.